This is the lesson video for 1-9, day 2 on graph transformations. Our goal is to be able to graph equations using what we know about the transformations of functions, specifically translations and reflections, but we will see a little bit with dilation in here as well. So that function that you see, the y equals, is just something that by the end of this we'd like to be able to graph using what we know about our transformations. So that said, we want to look at the parent functions we're going to be graphing, meaning the most basic form of the types of graphs we're going to expect you to be able to make. That said, the three are the graph of x squared, the graph of the absolute value of x, and the graph of the square root of x. And you made all of these in algebra last year. So by parent functions, we mean with no transformations happening to them, the most basic form of them. Without your graphing calculator, you need to be able to graph these functions. So if you need to, for the parent function, t-table these, meaning make an xy table and say that you know what happens for different values, both positive and negative, when they go into this, that works too. Here's what I know about x squared. I know that when 0 is squared, I get 0. I know that when 1 is squared, I get 1. I know when -1 is squared that I also get 1. I know when both 2 and -2 are each squared, that I get 4. Those 5 points are enough accuracy in order to get a reasonably good parent function shape. No fewer than 5 points on the graphs that have symmetry, please. The absolute value of x, same thing. If you would like to make a t-table and think through what those basic parent function points look like, please go ahead and do that. So when you think through absolute values, again, you want to check for some positive and some negative inputs because the domain includes both for the absolute value function. I know the absolute value of 0 is 0. I know the absolute value of 1 and -1 are each 1, so the graph starts off similarly to x squared, but I happen to know the absolute value of 2 and -2 are 2, so we have linear sides to the absolute value graph. And again, those 5 accurate points are enough to get me an accurate parent function. So I need to be able to identify on these first 2 graphs at least 5 ordered pairs from your graph that are accurate. When we do the square root of x, I know it has a limited domain. I know that the least value that I can put in for an entry under a square root is 0, and I know its square root value is 0. Then I would pick my numbers carefully. I know that the square root of 1 is 1. The next input I would do to get a nice accurate value on my graph is input my square root of 4, and finally square root of 9, which is 3. I would say 3 to 4 accurate points here, and for sure we need to know where your square root graph starts. Okay. What we're going to do then is explore a little bit, first with a calculator, and then you're going to need to be able to do this without a calculator, these different transformations. Actually, not GeoGebra, I apologize, Desmos. And what I want to look at is the different transformations that it's asking me about. So I'm going to split screen for just a moment. That first transformation asks me, what if I take any of those parent functions, f of x, meaning I could talk about the square root, I could talk about the absolute value, I could talk about any of those things. What if I were to take that and add something after the function? So on your graphing calculator, you could do this as well. But I'm talking about what would happen if I graphed something like that instead of plain old x squared. So I'm going to graph x squared in red, and I'm going to graph the new function for you. And you can just watch this on the video, and I'm going to add 2 this time. What I'd like you to take a look at when I pull the graph over is what transformation happened to the graph of x squared, the red one, to get it up to where the blue one is. And if I take that 2 off, or I change that 2 to something like 3 or -3, what happens to the graph? And your choices are any of the transformations that we've talked about. So I'm going to change this to a subtract 2, a subtract 1, a subtract nothing, and add 1, and add 2, and add 3. And what I'm noticing is that graph's vertex and all of its points seem to be sliding up and down. So when I see this graph of my function, and I could have done that with an absolute value or with the square root as well, whatever's happening there, when I add or subtract something after the function, after the square root or after the absolute value, this seems to be translating the entire graph up or down by as many units as we're adding. In class, we'll obviously do this a little more slowly, but as you're doing this on the video, you might want to pause the video, try that yourself on your graphing calculator, and just see that you get what we're talking about. I'm going to move over to the next set over here where instead of adding a number, we multiply that parent function by something in front. So I'm going to leave my nice red x squared graph, and this time instead I'm going to put a 2 out front and a 3 out front. And we'd like to figure out which transformation that 3 and that 2 are causing. So when I slide over and I see my red parent function of square root of x, and then I see twice that, I see a narrower parabola still anchored at 0, 0. And when I do a 3, I still see this even narrower parabola. And you might remember this from last year. I'm going to try a 0.5 in front just so I see what happens there. And I get a wider parabola. So of all the transformations, this is definitely changing the shape of the graph. It's stretching it wider or narrower. The larger the coefficient, the faster that x squared graph is growing in y values, so it's getting narrower. So this would be a dilation factor out in front if I multiply that. So I'm changing how fast or how slowly the parabola's y values are growing. Again, same for whichever parent function I'd be doing that for. My favorite one is this next one. If I take a function and simply put a negative sign in front of it, so I'm going to keep x squared, but instead of this 2, and I can almost animate it for you, so check this out. So if by putting that opposite sign out in front, I'm actually watching it, sorry, never gets old, I'm actually watching it reflect over the x-axis. So by putting that opposite sign in front of my parent function, it's a reflection over the x-axis. When I teach pre-cal and other classes, we end up calling that a ROX, a reflection over the x-axis. So to convince you that's not just with x squared, let's change this function to the absolute value of x, and then we'll also do its opposite. Let me just get that out of there. So there's my absolute value graph. Let me put that back in again. But again, this time let me put a negative out front. So you're seeing my reflection over that x-axis when I include that negative sign. All right, the final transformation that we're interested in then is what if instead I add or subtract something inside the absolute value or inside that square. So I'd be looking at something like the absolute value inside of x plus 1 or the absolute value of x minus 3. I'm going to put a number inside the function to see what happens. So I'll work with my absolute value graph. So you have the nice parent function up top. And I just put a subtract 2 in, and that red graph then is my new one, my image of my blue absolute value graph. And it looks like it was slid or translated to the right, okay, because my blue one is the new one. But that seems kind of funny. I put in a minus 2 and it went to the right. So all right, let me put in a plus something and see what happens. So let me put in a plus 3, and now that's in orange, and that slid it to the left. So as I can keep changing that number, and it keeps taking that absolute value graph and sliding it back and forth, left to right. So as I'm going to describe that transformation then, this is another translation, but this time not up or down. It slid my graph left or right, but what you might want to notice is this would have slid my entire graph or translated it left 1. This translated it right 3, as if it's almost opposite of sign. So looking here, let's see if we can double check that we get this, and you might need to look back at what you just had. If we take whatever parent function we have and add or subtract something afterwards, a plus k will slide it up k units. The entire graph, not just its vertex, every single point on the graph, does not change its size or shape. A minus k slides it down k units. So there's our translation. Our other translation, and I'm going to come down here, this was our other translation, so these two together are translations in different directions. So if we have the plus or minus inside, a plus h inside the parent function slid our graph left h units. That's the only one that's opposite of what its sign appears to look like, because the function has actually got a subtract sign in it normally. So if it's a minus in there, it's going right h units, every single point on the graph. If we change a number out in front, if we actually put a number out in front here, then whatever its absolute value is, meaning not worrying about sign, positive, negative, that's going to be a dilation factor. If there's an opposite sign in front, if our a value is negative, then that's a reflection over that x-axis. We'll save reflections over the y-axis for when you get into advanced algebra trig. Putting it all together, we have to look out front to decide if we need to dilate, which we're going to leave dilations alone for the most part, and or reflect over the x-axis, because we might have to do both. If it's a -2, there'd be a reflection and a dilation. This controls our left and right movement, and this controls our up and down movement. So we're going to test this out and see if we can graph by hand with a couple examples. So on this first one, it would like us to graph y equals the function, the square root of x plus 3. That x plus 3 occurs inside my function, my square root function, so therefore it's an inside function one. That's still a translation, but we're going to be translating the entire graph 3 units to the left. So we're going to take our regular square root graph, and we're going to translate every single point 3 units to the left. Now, to make my graph, what I like to do is I like to put my parent function points down, what it would be with the plain old square root of x, but since they're not my final points, I don't want to connect them and say that that's my final answer. So I'm just going to start with 3 points that would make up the regular parent function of the square root of x. Notice how I put them as x's, I did not put them as solid dots, they are not my final graph. If I translate each of these 3 points 3 units to the left and reconnect them, then I will have the correct shape and the correct position for all the other points in between on the curve. So my new graph, my final graph I should say, for the square root of x plus 3 will be that green graph that you see. All right, the second one has everything in it, every transformation we're going to expect you to be able to do. I have to take the parent function and reflect it over the x-axis. This is a translation of right 2 units, and this is a final translation of down 1. Now, order of operations wise, here's what I need to do. I need to think of what would happen to x so I do my transformations in the correct order. This is x, and if I plug the number in for x, the first thing I would do is subtract 2. So in my order list of what order I need to do these in, I would need to move right 2. Then after that absolute value, then I'd evaluate with that minus sign out front. So then I'm going to reflect everything over the x-axis. And finally, Aunt Sally, in order of operations, would say that the -1 at the end is the last thing I would do, so that's my last transformation. So I'm going to start with the parent function, like I did on my first graph. I'm going to start with that parent function, absolute value of x, just a handful of its accurate points put in. Each one of those points then needs to be moved right 2 units, so I'm going to take this first one right here. I'm going to move it right 2 units, so I'm moving right 2. I have to flip it over the x-axis, which means get to the x-axis and 2 more points over. And then even that point, which I was about to put right here, I've got to slide that down 1. So my final resting place moved to the right 2 units, flipped over the x-axis, and slid down 1. So that's my final resting place for that one. Kind of crazy. All right, my final resting place for this next one right here, it's going to have to go to the right 2, flip over the x-axis, and down 1. This one at the origin, it has to move to the right 2. As I flip over the x-axis, which nothing will happen, and down 1. When it flips over the x-axis, it's already on the x-axis. All right, at this point, to the right 2, flip over, down 1, you're starting to see your absolute value v form exactly where it needs to be my new function. And with your graphing calculator, if you enter that function and check the points, we have an accurate graph of that absolute value function. Make sure that if you have questions, you're requesting into resource, stopping by after school, and taking care of the things you need to so that this lesson feels comfortable and you're capable of carrying out the assignment. Have a good one.